Okay, we want to today nail the major aspects of alternating current circuits and the behavior of alternating current circuits. We start with a sequence of reasoning that we've amply experienced in lab. Okay, but want to pull it together. So we start with force on a charge, which comes from electric field. Now, the first time you saw electric field, it was in relation to a point charge and then line charges and cylindrical charge distributions and Gauss's law and all that stuff, okay? But you also know you can get an electric field by changing a magnetic field, okay? So in general, we just talk electric field gives you force and your charge, okay? And force on charge, well, the other thing is have a potential gradient associated with the electric field. The electric field is the gradient of a potential function. Right? And you can reason it out. You know, what are the units of electric field? Newtons per Coulomb. What are the units of potential gradient? Well, that's voltage, that's joules per Coulomb. If you divide joules per Coulomb by meters, etc., you need to understand all that. I'm not going to include that in this whole synopsis, but you need to understand these relationships. So you got a force and a charge in a conductor. Now I'm looking for the word. Come on now. Current density. I had the word potential bouncing around in my head. I could come up with the word current. You get current density in a conductor. Now, once you have the current density, how do you get the current? Well, actually, no, how do you get the current density? And the intermediate thing here is conductivity. So maybe I'll do this. Okay. And that leads to current. To Ohm's law without the idea that resistance is reciprocal of conductivity. But there are all kinds of other ways we can go here. We want to understand all these relationships and how they follow from one another. Okay. Then we have changing magnetic flux is one source of EMF. And that source of EMF, if we know the conductivity of resistance of a circuit and the EMF, we can figure out what the current is. Okay. So we jump from that. I want you to think conceptually about these, think in terms of the formulas, but think about what they mean and how you've experienced them in here. How did we experience the whole idea of potential gradient? We looked at the current and how it varies at different lengths of a piece of nichrome wire. Okay. The longer the wire, the less the current for the given volt. Okay. And the longer the wire, the less potential gradient. There's a connection there. So you want to think everything you've seen in lab and put it into your whole picture of what's going on here. Okay. Now, what we want to look at today. Say we've got current versus time. Okay. And this current is being produced by changing magnetic flux, where you're rotating at a constant rate. You're rotating a coil of wire between the poles of a magnet. Or if you want to make it harder on yourself, rotate the magnet within the coil of wire. Okay. Either way, you're going to get a changing magnetic flux in the EMF. And that flux is going to change sinusoidally. So that let's say your current is maximum current times the cosine of omega t. Now, what's omega? It's the angular frequency with which you're rotating that coil. Okay. All units, it's in radians per second. Now, we do some funny little stuff between radians and degrees, because a lot of times we'll say this current is 90 degrees out of phase with that one. Okay. It's easy to think 90 degrees. We just think here it's 0, here it's 360 degrees, here's 90, here's 180, here's 270, right? Makes it easy to think, well, there's 2 pi radians, so there's pi over 2 pi and 3 pi over 2. But the numbers for the degrees are somehow more intuitive and don't involve fractions. So it's easier to think sometimes in terms of 90, 280, 270, 180, whatever. Okay. But you got to know 90 degrees is pi over 2 radians and so forth. And you do. I don't think that's a problem for you at all. Okay. Well, that's great. Now, it's Q sub cap. A little hard to read that cap. Just charge on a capacitor. Okay. can you sketch me a graph? If your capacitor is initially uncharged and this current starts flowing in your circuit, can you show me what the charge on the capacitor is? Can you show me what the graph of the charge on the capacitor would be? You've charged up capacitors with the cranking generator. You know that the easier it gets, the more the less current you're producing, because it takes energy to produce current. And if you're creating energy by cranking at a constant rate, it means you're exerting a force. And the more energy, the greater the rate, the more power you're producing, the more force it takes. Okay? And that's associated with current. The more force it takes, the more current you're driving. The other thing is, if you're cranking at a constant rate, then your angular frequency of the rotation of that coil within the magnetic field is going to be constant. So you're going to be getting constant voltage, right? But you're not getting a constant current, are you? If you crank that thing forward, it gets easier. Okay. Then if you reverse it, surprisingly hard at first, and then it gets easier. Then if you reverse it, it's surprisingly hard, and then, okay. So can you put all that together and tell me, along with the idea that a capacitor consists of a device in which you can transfer charge from one region to another, which then creates an electric field, which some voltage looks like. Okay. Okay, now, I'm not sure I've seen a correct graph, which doesn't surprise me that much. I think, even though I pretty well nailed my sophomore level E&M course, at the stage when I first was looking at AC circuits and somebody had asked me this question, I'm pretty sure that I, along with 75% of my class, which was mostly physics majors in a very highly rated school of technology, science and technology, would have gotten it wrong too. So if you get it wrong, you got a lot of good company, well, bad company in my case, but good company in the rest of my fellow students. Okay. So I'm going to ask you a simpler question. What part or parts of this cycle would the, charge on the capacitor be increasing? From what part of the cycle to what part of the cycle? And you can even do it in, well, gradient pi. Here's pi. 3 pi over 2. And pi over 2. For each of these segments, is the charge on the capacitor increasing or decreasing? And is that consistent with your graph? Your graph is almost certainly wrong. So don't go by what your graph of your capacitor charge is telling you. Go by what happens between the source and a capacitor and the transfer of charge and current. Okay, now this might cause us to have to reverse our thinking, and I kind of think, well, I didn't make a decision on this earlier, and I should have, but I'm going to say the charge in the capacitor is the charge on, let's get the arrow right, on this plate right here. Okay. So if the current's flowing this way, this plate is going to be positively charged, right? So tell me where it is that the charge on the capacitor is going to start decreasing. Or tell me for how long the charge on the capacitor will increase. Okay, so I say the initial charge in the capacitor is, well, I really don't want to say that, okay? Because if I do, we're going to have to deal with the transients, how the current smooths out after a number of cycles, okay? And you've seen transients, I think, in differential equations, maybe, okay? So you're going to be equipped to handle them, but I'm going to modify what I said. I'm going to say, I want the charge to start out, or the voltage on the capacitor, start out negative, which means that I really want to be looking at this plate, okay? Because when this plate has positive charge on it, the capacitor is pushing in the positive direction, okay? So we're going to assume that this plate starts out with a negative charge on it because, well, you see, okay, so what happens is between 0 and I/2, the charge is increasing, okay? And what actually happens is it starts down here and it ends up here. Its peak charge is going to occur when you're no longer pushing positive charge onto the capacitor, okay? So this phase, when you're pushing charge onto the capacitor, here it is. It starts out not building very much because you don't have very much current. Your current maximizes here, so you're pushing charge onto the capacitor at the maximum rate, which means your charge is going to increase most rapidly there, okay? Your current's going to resist. It's going to go, your current's going to reverse. It's going to go in a negative direction, which is going to start pulling charge off the capacitor. Okay, of pushing opposite charge onto the capacitor. So from here to here, does, okay. So I'm going to use a little color here. Charge is increasing over this part of the curve, right? And then sorry, this chalk is just not behaving very well. The charge is now decreasing over this part of the curve, right? So that here again, charge increases. Again, slowly at first because you don't have much current. Most quickly here, we have the steepest graph, and more slowly here, where it levels off before it starts to decrease. That makes sense? Okay. So this one peaks later than this one. So they're out of phase. The voltage on the capacitor is out of phase with the voltage, with the current, okay? We'll think in terms of current. So we put these two graphs together. like so. It helps to sketch the quarter cycle lines. So here is I, and here is your capacitor voltage. Your book uses a greater amplitude for the capacitor voltage, but since this is voltage and this is current, you can choose any relative scale for the two. So now this is voltage of the capacitor, which we would identify this plate. I think I'm pointing to the wrong plate, so let's just not point to the plate. Okay, I think that's good. That makes sense? So the capacitor voltage lags the current. Think about it. You're cranking until it gets easy to crank, and then you reverse. Okay, why is it harder to crank at first when you reverse it? It's because there's still charge on the capacitor that's fighting it. Before too long, it's about as easy to crank as it was when you started. Okay, and then after a little while, it gets really easy. Then it's time to reverse it again, and you fight it. The voltage in the capacitor is always 90 degrees behind this because, again, when you first reverse it, the capacitor still has charge on it. It still has its voltage. And that voltage doesn't decrease to zero quarter of a cycle. Okay. Reconcile that with your tactile experience. So you know what it feels like. Okay. You'll understand this much better if you relate what it feels like, what's going on. Okay. Now it turns out that with an inductor, it's happening with the back EMF. EMF inductor. And we could call this the EMF of the capacitor. And actually I use B here, could have used EMF. But in any case, what's happening to your inductor here at the first cycle? Okay, again, if this is your current through the inductor, okay, then the rate at which the current changes gives you back EMF, right? Now, going to take a back EMF as being positive. You'll see in a minute when we set up these circuits, okay? But what's going to then happen is, okay, your di dt maximizes here. Minimizes here. Okay, rate of change is greatest here. So the EMF increases most rapidly here. And I'm setting this up wrong because I should, no, I shouldn't. Hang on a minute. I have the picture not the way I wanted it. Okay, because I want the initial EMF to be zero. And that's only going to occur if I start the graph either at this point or this point where the rate of change of the current is zero. Okay, because remember the EMF across the inductor, the back EMF is the rate of change of flux, which depends on the current. If you've got a current that isn't changing, you're not going to get any back EMF. You're not going to induce any EMF around the loop of whatever it is you're working with, okay? So here, the rate of change of the current is zero, so the EMF is zero. Okay. Here, the rate of change of current is maximum. So the EMF is going to be maximum. So at pi over 2, you get the maximum of this. And then at pi, you're back to zero. So at t equals pi or whatever. And let's say that let's label this axis omega t. It's actually a good idea. Because then the 2 pi makes sense and so forth. Okay, so when omega t equals pi, this thing's back down to zero. And then when omega t is 3 pi over 2, we have maximum negative inductance, EMF and inductance, right? Back EMF. And when we're pi, we have this. So the graph is going to look like this. Now you see the peak of the induced EMF, back EMF, occurs before it does for the peak of your current. Okay, when the current is changing most rapidly, that occurs before the peak. Or it's not changing it. Okay, when you have the greatest rate of increase of the current, you have the greatest back EMF. And the back EMF then gets its peak 90 degrees phase before current itself reaching its peak. So we have a graph looks like this. Well, So you have see, you have that EMF as a function. See, so L usually what the book uses B sub L. BL is 90 degrees ahead of I. Capacitor is 90 degrees behind pi. It's a 90-degree lag here and the 90 degrees ahead here. That make any sense? You want to think in terms of the details of the inductor and the capacitor. And I'm being a little loose with plus and minus signs. I think I'm making mistakes by trying to be consistent with what you looked at in two different sections. Okay, because your book is giving the same expression for the voltage across the inductor as it does for the voltage across the capacitor. And they're 180 degrees out of phase. Okay, and I'm not getting those phase differences from what I'm seeing in the text. And I'm trying to reconcile that. And I just realized with a closer look at the text that either I'm completely confused, which is possible, or the text is using different notations in different sections. Okay? Now, really comes down to this, Kirchoff's laws, we've been over it. We have voltage drops from one point of the circuit back to the same point. Okay? Whatever the EMF of the source is, we're going opposed to the source when we do this, and we have negative EMF of the source here. We have positive voltage change across the capacitor, which is Q over C, that's voltage capacitor. Voltage change IR across the resistor. Voltage drop IR, okay? And your voltage drop is DI, LDI, DT across the inductor. And we talked about all that in some detail when I wrote out the original equation. Now, you're saying that some of you that it's kind of easier to use calculus too on some of this. Well, yeah, the book kind of approaches it that way, and you're okay to use the book because they just kind of quote formulas that they haven't really derived, but sort of. Maybe they really have. I want to look closer at what in the world they're doing. But what you end up with is, I think you'll understand this in terms of what we talked about, why the capacitor lags the voltage, the current, and why the inductor is in advance of the voltage. Okay. So again, you get the equation when you sum up symbol. But there it is. You got the EMF of the source, which you could call B source if you wish. Okay. And we're assuming that the source is the result of rotating a loop at constant angular velocity within a magnetic field, everything being lined up perpendicular and so forth. Okay? Since the current is the derivative of the charge in the capacitor, this equation. The homogeneous equation, if you just let Q equal Q naught e to the RT, homogeneous means set the right hand equal to 0, you get this simple equation. You get this. If this discriminant is negative, in whichever way you rearrange things, if this is negative, you have oscillatory behavior. Okay? And that leads you to the solution. Q equals Q naught e to the negative R over 2LT, e to the I omega t. This solution turns out I don't want to use Q naught here. Um, I'm going to use a capital C, but I can't use a capacitance. Alpha, because it's going to disappear. So we end up with this. That's our Q of T. And it comes out just by turning the crank. You have an exponentially decreasing function. is constant, negative R over 2L. You have a cosine of omega t plus phi, where omega matches the omega of your source. Then I equals dq dt, which is omega q naught Okay, in the case where R over 2L is 0, that would be the ideal case where you have no resistance, which is the case we're looking at here, at least for the moment. Then your current is omega q naught negative omega q naught times the sine of omega t plus phi, and di dt is negative omega squared q naught cosine of omega t plus phi. The sine and the cosine are 90 degrees out of phase. The negative cosine and the cosine are 180 degrees out of phase. This leads you to a picture that we'll talk about next time, which is this, called a phasor diagram. Okay. This is a voltage across the resistor. This is a voltage across the inductor and a voltage across the capacitor. One will typically be bigger than the other. Maybe the resistor is missing. Okay. But we imagine that this whole picture, these three vectors are rotating with angular frequency omega around the origin. This is 90 degrees in front of the voltage across the resistor, which is 90 degrees in front of the current. This is 90 degrees. The circuit being driven by whatever frequency. The frequency is the driven source. Okay. And the vector sum of these three tells you where current really where the current really is. Okay. So in this case, if you add this to this, say this is a little bigger than this. So we take this and we add this vector, and then we add this vector, we get this vector, which is our current vector. Okay. So our current is out of phase with our source. This will be in phase with the source. And I didn't say that right, but you end up with a phase difference. Okay. If you have just a resistor and a capacitor, it's like the first thing we looked at, where you don't have this. Okay, so the voltage, there's the current legs. Well, the capacitor voltage stays in front of the current. We have to do more explanation to understand that, but understand those first two diagrams we talked about, and understand how this is a diagram of an LRC circuit. And next time we'll try to pull this together. I got mixed up just by looking at the text where they had the same expression for the voltage across the capacitor as for the voltage across the inductor. Okay. Then later, they pulled all of this stuff. Okay, I think. Now that my perception could be what's at fault, because the book is very well written. And I did get a little confused there. So we'll go on with this next time.